Dear colleagues, I'm very glad to present our research regarding discord discovery in time series, or can we detect all anomalies of an anomalously long time series in an anomalously short time. In Russian, поиск диссонансов во временных рядах, или можем ли мы найти все аномалии в аномально длинных временных рядах за аномально короткое время. Aside all, thank you very much for organizers who didn't let me forget the topic of my research, of my talk, just because the summary of the talk was the biggest one among all the summaries of keynotes. Well, at first, let me make some disclaimer. Actually, this very talk doesn't touch deep learning anomaly detection at all. But the authors acknowledge that deep learning plays an extremely important role in modern DAMDID in general, and in time series analytics in particular. However, we believe that in time series anomaly detection, just a simple math is at least competitive with the deep learning approaches. And don't be afraid, during our research, neither deep learning model or deep learning scientists were injured. Well, people like to measure everything over time in all domains, and there is a fact that in random sample or of 4,000 images in 15 newspapers from different countries for the respective period, more than 75% of images are time series. And we do know that time series are ubiquitous. It is about weather, electrocardiogram, exchange rate, even average happiness, and national debts, Shrovetide pancake prices in Russia, and so on, etc. Your time series can be here as well. But in time series, people are most interested in anomalies. You can see the plot from the following paper that scientists are interested in time series anomaly detection much more than other types of data, images, text, video, etc. So what anomalies we're interested in? At first, we should say that it is not about peaks or valleys, just single outliers that are very dissimilar in the global context or within their neighbors. We actually interested in subsequence anomalies. It is the challenge. Just because in subsequence anomalies, the collective behavior of points can be anomalous, but at the same time, a point may not be an outlier, just like here. We do know that anomalies are very informal and domain dependent. Actually, the classical definition is about anomaly is an observation which deviates so much from other observation as to arouse suspicion that it was generated by a different mechanism. So for Russian background, we do understand that right here, Quasimodo is actually an anomaly, but at the same time, we are not sure that turnip is an anomaly as well, just because of our background, because of our fairy tale about turnip. Well, so there is a discard concept that formalizes subsequence anomaly. It is intuitively defined as a subsequence of the given length whose distance to its nearest neighbor is the greatest. This very concept was proposed by the American scientist Eamon Keogh. And we should note at first that this very concept is agnostic, that is domain independent, and it doesn't demand learning at all. And second, this very concept is exact, that is the Discord discovery outputs determined result, and it is reproducible. Well, let me illustrate the discard concept at the following example. We consider the persons from the Simpsons story, where each person represents some subsequence of the time series. You can see the differences, the distances between the persons, and actually you can see that Quasimodo is actually very distant person. At first we establish the distance matrix. The idea is very simple. The close neighbors, the similar they are. And after that, we calculate all the distances to neighbors, like here. And the next step would be we calculate distances to nearest neighbors, that is columns-wise minima, you can see. And after that, we are to find maximum among column-wise minima, so the farthest distance to the nearest neighbor. And finally, the argument of the maximum among column-wise minima will be the farthest nearest neighbor, and it is Discord. We should say at first that discords are not always identical to anomalies. Here are an example. It is electrocardiogram excerpt where the professional cardiologist determines the arrhythmia case, and you can see that it is actually not the same as Discord found of 75 points. You can see there is very distant Discord's nearest neighbor, and here you are the distances to nearest neighbors. So discords just reflect anomalies in real life, but are not identical. Here you are one more example. It is about average speed in Guangzhou, China, where we tried to find top discords of the same length, and you can see that the top discords are actually almost at the same moments, with some abnormal events, just like Top one was Mid-Autumn or Lunar Festival. Top two was coincided with Typhoon Nida. And the top three Discord was about a long weekend devoted to Day of Victory over Japan. However, for long time series, we do need all length subsequences, anomalous subsequences. Here are one more example where we can see anomalies of different length within 2-year power demand from one China electrical company that illustrates some problems with electricity equipment. So our problem is transformed to discovery of all length anomalies. That is why we do need slight changes in the discard concept, and it is range discard. Range discard is actually a discard that is at least at some threshold far away from its nearest neighbor. So we are given sometimes series and a range of discard length. And after that, we are to find the set of subsets where each subset contains discord of the specific length, just like that. At this slide, I depict the roadmap regarding time series discord discovery algorithms. The original algorithm was coined in 2005 in the respective paper, and after that it was prolonged with the drag algorithm and Merlin algorithm, which discover single length discord and all length discords respectively. And these are development from Iman Kyo and his colleagues, and here you are parallel algorithms where PD3 is about fixed length discord discovery, PALMET is about all length discord discovery, and the PADI algorithm is about all length discord discovery, but this very algorithm is about discovery on multi-GPU HPC cluster. Let us consider how the discovery of fixed length discords works. It is about two phases. The first one is selection, where we are to scan our time series and create a set of candidates to discords, and the second phase is refinement, where we have to discard false positive candidates. How the candidate selection works? This is very simple algorithm. You can see the pseudocode. We initialize the discard candidate set with the first subsequence of our time series, and after that we move the sliding window from the left side to the right with the step 1 and get the current subsequence, and for each candidate we just calculate the distance between the current subsequence and each candidate, and if it is less than the threshold, the given threshold, actually we should discard, we should exclude this candidate from the candidate set. But if finally the current subsequence is valid through all checks, we should include this subsequence into the candidate set. So we move forward, and during the moving, we can exclude the previously found candidates, just like here, X candidate was excluded. So at the end, we may have the situation that some candidates are false positive. You can see right here that subsequence is actually false positive, just because the distance between Z and V and Z and X is less than the threshold, and we cannot find this situation. We cannot catch this situation just because V and X were excluded previously. And we should establish the second phase about discord refinement. It is very simple. At first, we should assign the final discord set as a candidate set and move the sliding window from the left side to the right of the time series with the step 1, and get the next subsequence. And for each candidate from the candidate set, we should calculate the distance between candidate and current subsequence. And if it is less than R, the given threshold, such discord is false positive and must be pruned, just like here. So at the end, we discard that subsequence as false positive. Well, what's wrong with such algorithm? Two things. We should note we have to select our threshold manually, and we have to select discard length manually. Here are the illustration of such problems. You can see that if we take our threshold too big, we miss some discords. Here you are an example of average number of passengers in New York taxi in 2014. And you can see if the threshold is too high. Just let me remind, this is the distance between the subsequence and its nearest neighbor. So if this threshold is very high, then we should miss some discords. So on the other hand, if our threshold is too small, we got false discords, just like here. You can see we do have false positive. One more thing, to discover all discords, we unfortunately must to test all the values of our discard length. Here are some example. We do have two synthetic time series, and we can see that these very pseudocodes are about to create such time series, and we can see that we can correctly find a subtle anomaly for some value of the discard length, but for m+1 it is impossible. And at the same time, for the second time series, we can correctly find a subtle anomaly for the same length, but not for this length -1. So we should check all the lengths. And the Maryland algorithm was an answer to such problems, where the threshold is adaptively calculated. This is the actually basic idea of this algorithm. Keogh and colleagues just invented that the threshold must be calculated differently for different length of M. They just empirically found that the threshold depends on the previous four length of the previous distances between discords found and their nearest neighbors. And right here, NN is actually the respective distance, and mu is average, and sigma is the standard deviation. So that is just simple math I noted at the starting slide. And here you are the diagram of the Maryland algorithm. You can see the interval of lengths is divided on 3 parts, and we calculate the initial value of of the threshold and differently, as well as adaptively change this threshold after the discord, if the discord were not found with such a value. So this is very brilliant algorithm, but what is wrong with Maryland? Actually, it is serial. It is not parallel. Being parallel, we could find the anomalies much more effectively, and it has redundant calculations. Just the algorithm computes the Euclidean distances between candidates and subsequences over and over again along the moving sliding window, and it can be done actually more effectively, we can see. So the answer to the first question, how can we discover discourse in parallel? Will it work? The simple idea, just can we take our time series, divide by the nodes of our HPC cluster or cores of our CPU or GPU, and after that select and refine discords within the single node, and after that just combine the results? Unfortunately, the answer no, just because of this very simple example. Just like here, we, as previously, calculate the distances between our subsequences, and we can find the discourse just like here within each fragment of our, within each part of our time series. And you can see that we do have top 1 and top 2 discords. But if we look more attentively inside, we can see that indeed the top 2 discords is actually the false positive top 2 discord, just because the true positive top 2 discords is in the first part of our fragmentation. So what did we do? we found that the parallel discord discovery should involve global refinement. So at first, we should divide our time series into fragments as previously, but with some overlapping, just not to lose the results at the junction of the fragments. And after that, we should perform local selection and local refinement within each fragment. But after that, we should combine the results and establish them as global candidates that should be globally refined. They must be sent to each node and refined globally with respect to all partitions. So just at the end, we should perform intersection of the partial results to have global discourse that is discourse with respect to all partitions, and it will be true answer to our problem. So at second, how we reduce costs, how did we reduce costs at the distance calculations? We did use the special distance function. It was Z normalized squared Euclidean distance. It is very simple. Everyone knows what is Euclidean distance. And actually, as for squared, it is very simple. It can be calculated more effectively than square root, for sure. As for Z normalization, it is about unifying our subsequences just to not to take into account amplitude of our subsequences, but more the thing that is more important, that Euclidean, the squared Z normalized Euclidean distance actually is closely connected with the Pearson correlation. You can see the formula. This very formula involves the scalar product of our subsequences, you can see, and mu and sigma that are averages and standard deviations of our subsequences. And this very formula helps us to reduce costs of our calculations between subsequences. So we derived the following formula and calculate distances between subsequences with the lengths within that range. According to this formula, it reduce the complexity of calculations from big O of M to the big O of O1. So we employ the ideas above and established two-level data parallelism, where we divide our time series between disks of our HPC cluster, that is fragments, and within the memory of each GPU, within a node, we perform segmentation in the same way with overlapping. But this segmentation is about the division of data within the main memory. So after that, we slightly modify the classical scheme of the Merlin algorithm, you can see, but the calculations are performed both on GPU and CPU, you can see. And we also add a stage of pre-processing where we calculate averages and standard deviation just to reduce costs of calculation distances between subsequences. Well, here you are the pre-processing phase, just a couple of words. This very formulas helps us to calculate distances more effectively. And after that, here are the overall scheme of our calculations. We just go inside from upper level to the down level. You can see right here for exchanges, for data exchanges, we do use message passing interface that helps us to communicate between nodes with candidates. And finally, master node performs global refinement. And after that, we will see how we select and refine the discourse with respect to the fragment. The schema is actually the same as previously, but all the data exchanges are implemented through the main memory of the central processor of the node. And after that, they go further, and we will see how we select and refine discourse with respect to this segment. Actually, this is the PD-free algorithm. We just take the fragment and divide it in two ways. At first, by sections, and then second, shifting right to the shifting to the right to the length of the discourse, and we derived the following formula that helps us to substantially reduce costs of calculation of the distance between subsequences. Right here, you can see that the redundant elements after the shifting are zeroed, just because we should establish the correctness of our calculations. And as for refinement, it calculated in the same way, but we take the subsequences not to the right but to the left of the section. So we perform discourse refinement, and the final stage of refinement with respect to the whole time series is performed as follows. We establish the distance, so-called distance matrix, and discourse bitmap. We prune the candidate if the minimum distance in the rows of such matrix is less than the threshold, the squared, just because we did use squared distance. And after that, we perform the blockwise matrix multiplication between segments and transposed candidates. And finally, by doing so, we do have matrix of scalar products of our subsequences, and this helps us to calculate the distances through that formula I showed at the previous slides. And finally, we do have the distance matrix. So that is all about our algorithms, and few words about experimental evaluations of our algorithms. We involved two HPC clusters, one from Nizhny Novgorod, Lobachevsky, up to 64 nodes with Kepler GPUs, and from Moscow State University, Lomonosov 2, up to 64 GPUs with Tesla P100 GPUs, and HEUA 2 time series, 2 million length each one. And we try to find the discords of length in the following range. It was electrocardiogram and annual household power consumptions. We measured performance. It was average running time and speed up. Actually, the ratio of performance on one and P GPUs respectively. So here are the results at Lobachevsky HPC cluster. You can see that our algorithm is has sublinear speed up. You can see the ideal speed up is a line is higher, but this is very good result, just because we do not have a deterioration of the speed up, and we cannot avoid sublinear speed up just because of overhead of exchanges between nodes. So we must send our candidates from each node to each other node, as I showed at the previous slides. And as for runtime, as for performance, you can see that at 64 GPUs, we can find from 2 million candidates, we can find approximately 1,500 discords in less than 1 minute. And the same picture is regarding the speed up and performance on Lomonosov 2 HPC cluster. We do have sublinear speed up and very good performance. And at the end of our talk, I'd like to show some case studies. It was the first one is about HPC cluster workload at Alibaba Cloud. This is platform for artificial intelligence. We just took this very time series and tried to find discords with range in 3 to 7 minutes. And you can see the results. Obviously, they indicate that something went wrong. One more example is about eBay HPC cluster workload. The same history, actually the similar history. This is pooled solver metric of eBay application solver. Obviously, obviously that the discords show us that something is not normal. One more case study. It is about smart heating control. This is just the temperature in some lecture hall in my university, where we do have a temperature sensor with frequency 4 times per hour, and we just find some discords you can see, and obviously there are some problems with either sensors or with a system administrator who treats these sensors. One more example regarding heavy industry. It is about cold roll mill stand. It is about the system that makes it possible to have plain steel sheets. There is some continuously variable curvature system within the mill stand, and there is some problem that the plates of a CVC system destroyed very often. We just found the discords in the time series of bending force. Obviously, there are some reasons to change these plates because of abnormal situation. And the final example is about the very, very long time series. You can see it is about solar energy production in Australia. This very time series is about frequency once per 4 seconds. It is 7 million time series, and we tried to find top discords by means of our algorithm. You can see the results. Actually, maybe some specialist in this very domain can explain these things. The only thing I discovered in the scientific literature that geomagnetic storm is actually almost coincide with August discord at this picture. We do not know the reasons, but we do know where the anomalies are. So, dear colleagues, this is almost all. We are ready to discover all the anomalies in your time series as soon as possible. The rationale from my talk, Discord formalized time series subsequence anomaly. I presented a serial Discord discovery by Iman Kiok and colleagues, Drag and Maryland algorithm, and our research that are the only and scalable parallel algorithm regarding Discord discovery, PD3, Palmat, PEDI, that are our algorithms. So thank you very much for your attention. We are ready for your questions. Please use this microphone.
As a chemist, I thought about chemical application of your very interesting approach. Now, for example, the chemical analysis of city hour in time. Does your approach allows a determination of size anomaly, размер аномалии. Не только ось абсцисс, но ось ординат. Ну, например, ПДК. Ну, содержание примеси в воздухе.
It's not a big deal. Let me get the auditory back to my slide. One at the very earliest slide. Just a second. Yes, this one. See, this very concept is applicable for any subject domain. So discords can be applied to the chemistry, to the transportation, to the seismic research, metallurgy, solar energy, etc. in many domains, just because this concept is agnostic and it is exact. This is about simple, strict, proven math. We believe it is possible. Maybe the only problem, we are able to discover discords, but we do need someone who will explain the discords found. That's my answer.
Okay, thanks for your talk. I would like somehow to discuss the application area of these methods, algorithms, and so on. As we can see, you provide a lot of examples, a lot of application areas, but okay, I can, for instance, try to divide these examples into two groups. So first, you can apply your methods if you have a huge history contained in some area, and the opposite case is then you are trying to analyze the real-time time series. So the question is, from your experience, what is the most how can I put it, the most usual use case? This post-analytics of huge time series or real-time analytics. And the second position is, okay, you do provide some means to execute your algorithms on clusters. But for instance, when we see some EEG data, then I doubt that some regular hospital can support some cluster. In this case, I rather think that they can obtain some just notebook with some one GPU. And again, okay, it's very different use cases. And again, from your experience, what do you think? What is more usual for the real world? This cluster case or just notebook with GPU case?
Thank you for very good questions. Well, at first, for sure, we cannot discover anomalies if we don't have enough time series. Next, indeed, both situations are typical when we do need post-analytics and we do need discovering anomalies online. This very talk was about the case of post-analytics. However, we do have one more development. This is ongoing research, and it is about the online discovery of anomalies. Right here, we do use our algorithms regarding Discord discovery, plus our algorithms regarding the discovery of typical subsequences within time series. I just prepared about 10 slides about this topic, and we can discuss this after the. But it is very interesting topic. As for the third sub-question regarding the platform, right? Not each hospital can provide us with a HPC cluster, but we can hope on this. Maybe just as an cloud service, but still, PADI algorithm is about HPC cluster, but PD3 and PALMAT algorithms are about just simple GPU, just single GPU. So we believe it has a wide spectrum of applications within our ordinary life. Thank you very much. We would be glad to communicate, to collaborate with everyone who interested in discovering anomalies in time series in your subject domain. Thank you.